Hello, my name is Pritish Chandna. I am a PhD candidate in the Universitat Pompeu Fabra in Barcelona, Spain. Today I will be presenting my work on content-based singing voice extraction from a musical mixture, done in collaboration with Merlin Blau, Jordi Bonada, and Emilia Gomez as part of the Music Technology Group in Universitat Pompeu Fabra, Barcelona, Spain. This work was supported by the Towards Richer Online Music Public Domain Archives or TROMPA project, and this presentation is being made for the International Conference on Acoustics, Speech and Signal Processing 2020. As the title suggests, we propose a system to extract a singing voice from a musical mixture. While music doesn't necessarily have to have vocals, in this case we define a musical mixture as a combination, linear or otherwise, of a vocal stem and other musical instruments. Now, the vocal stem may refer to the dry, studio recorded vocals plus any effects which were added during mixing or mastering. Now, separating vocals from mixer has long been a topic of research in the signal processing community. Indeed, over the last few years, a number of deep learning based algorithms have been proposed which have raised the bar in terms of performance. Most of these algorithms focus on separating the vocal stem from the musical mixture. Last year, we proposed a methodology to resynthesize the vocal signal in a musical mixture by estimating synthesis parameters via a deep neural network. In this presentation, we propose an improvement to our previous work by synthesizing the vocal signal from the underlying linguistic content present in the input mixture. Before proceeding further with the methodology, I would like to present a real-world example of a musical mixture with processed vocals. The future is coming on, it's coming on. As you could hear, this musical mixture comprised of a vocal track processed with effects like reverb, combined with a backing track comprising of drums, bass, and guitars. Now let us see what happens when this musical mixture is passed through one of the recently proposed deep learning based source separation algorithms. In particular, we will be using a pre-trained version of the WaveUNet, which we understand is not the state of the art. We are not making an argument about that. We are just using it as an illustrative example for our presentation. The future is coming on, it's coming on. As you could hear, the output of the algorithm had some interference from the backing track, in particular the hi-hat and the snare of the drums present in the musical mixture. Now, this interference varies from algorithm to algorithm, and you might find that the interference in one particular algorithm is lower than the interference in another algorithm. However, you would also have noticed that the output is still the processed vocals which were present in the musical mixture. Now, let us see what happens when the musical mixture is passed to the algorithm that we are proposing. The future is coming on, it's coming on. You could see that the output is a resynthesized version of the vocal track present in the musical mixture. You would have noticed that there is no interference from any of the other instruments which were present in the musical mixture in the output. In addition, you might have noticed that the fundamental frequency, or the F0, was slightly different from that which was perceived in the musical mixture. In the next slide, I will explain to you the methodology and why such errors occur. How does it work? Well, our system takes as input the magnitude component of the spectrogram of a musical mixture. This is passed through an encoder network which computes a continuous representation of singer-independent linguistic features present in the input. This representation, along with singer identity, which could either be a one-hot encoded vector or a learned embedding, is provided to the decoder, which generates the spectral envelope for synthesis. We use an external polyphonic F0 extraction system to extract the pitch from the input, which, together with the spectral envelope, is used for synthesizing the raw vocal signal. Our initial idea was to use explicit linguistic representations like phonemes. However, this approach was hindered by the lack of a sufficiently large annotated dataset and the linguistic constraints imposed by such an approach. Instead, we decided to use an abstract representation of linguistic features, such as the one used in voice conversion systems. One such system was proposed in ICML last year, titled AutoVC. This system suggests that an autoencoder with a sufficiently small bottleneck can learn to disentangle content from speaker identity. We use the same architecture as proposed in the paper with one exception. We use world vocoder features as a representation of the vocal signal instead of the MEL spectrogram as proposed in the original paper. The reason for this is twofold. Synthesis via vocoder features is easier than through the MEL spectrogram, which would require a resource-intensive auto-regressive neural vocoder. In addition, the use of world vocoder features allows us to disentangle timbre from expression, which is important in the case of singing voice to retain the melody. For training, we use a proprietary dataset provided by Yamaha Corporation. This dataset consists of 205 songs with 45 distinct male and female singers, leading to 12 hours of data. Most of the songs were English and Japanese pop songs with backing track present. We used a 90-10 split for training and validation, which we used for early stopping. For testing, we used the MedleyDB dataset, which is a publicly available dataset, consisting of 122 songs for which both the raw audio and the mixing stems are present, making it ideal for our case. We used 6 of the songs for subjective evaluation, and to the best of our knowledge, there is no overlap amongst the singers in the training set and the singers present in MedleyDB. Training is divided into 3 phases. In the first phase, we pass the spectral envelope X to the AutoVC architecture, which decomposes it into the content embedding CAVC. We then train a singer-dependent network termed as SDN to replicate the content embedding CSpec, given an input mixture spectrogram. The decoder of this network is fed the singer identity as a one-hot vector and regenerates the spectral envelope X hat. Finally, we train a singer-independent network, or SIN, which is similar to the SDN but learns the singer identity implicitly from the input spectrogram. The architecture for both the SDN and the SIN is the same as the architecture proposed in the AutoVC, with changes to the input and output layers. Evaluation in our case is a bit tricky. A direct comparison with other models via objective measures like BSS eval is not feasible. This is mostly because the output of our system is a resynthesized version of the vocal track. Instead, we had to use subjective listening tests to evaluate 3 main aspects of the output: intelligibility, isolation from the backing track, and audio quality. We compared 4 models in our evaluation: the singer-dependent network, SDN, the singer-independent network, SIN, a baseline which we refer to as UNET, and the model we proposed last year which we refer to as SS. We used an online A/B listening test wherein participants had to pick between 2 examples on a given criteria. Each criteria had 15 questions with 5 questions for each pair. There were 25 participants in our listening tests from various countries, even though all participants proclaimed proficiency in the English language which was used in the test. We can see from the results presented here that the SDN and SIN were ranked higher on intelligibility than our previously proposed model, the SS. This shows that the content encoder we propose is able to effectively learn the underlying linguistic features from the given input spectrogram in a singer-independent manner. We also see that all 3 synthesis models outperform the mass-based model on isolation. This follows from our previous observation last year. We also see that the models we propose lag behind on audio quality. This can partly be attributed to the degradation during synthesis and errors in estimation of the fundamental frequency, which is done via an external model. And now we come to the fun part of the presentation. We have presented a methodology to extract the unprocessed vocal signal from a musical mixture based on the underlying linguistic features. While it requires some future work, some of the applications that we have in mind include removing effects from a vocal stem. Here we can listen to an example. No one's gonna take me alive. The time has come to make things right. So here you can see an example of a heavily processed vocal stem which has been mixed with a backing track. Let us see what our system outputs. While you can see there are some errors in estimation of the F0, the output is quite intelligible and the lyrics are quite similar to that of the input. Let us now take a look at another example of synthesizing a single voice from a unison, which is quite often observed in choirs. This is an example of three singers singing in unison a song in Catalan, a language which was not seen during training. Let us see what our system outputs. Of course, it requires further research before any practical application can be proposed, but it is a good example for the moment. Let us now take a look at a more extreme example of converting growling vocals to a clean singing voice. Keep in mind that growling vocals do not have a F0. Well, of course, it was not easy to understand, but for people who are familiar with the song, the output is as intelligible as the input, which might be the case for all of us. Anyway, going further, other applications include transcription, which basically consists of mapping the linguistic features to explicit linguistic features such as phonemes. Of course, it can be used for voice change, pitch correction, and even remixing. We present some audio examples at the website listed here, as well as the code, which is also listed here. However, at this moment, we cannot publish the trained model because the dataset used for training is proprietary. All the examples shown in this presentation are real-world examples wherein the input singers were not seen by the model during training. The Titan X GPU used in this research was donated by the NVIDIA Corporation. The work is partially supported by Towards Richer Online Musical Public Domain Archives, or TROMPA, and the dataset used for training was provided by Yamaha Corporation. And I guess that's all. Thank you, and any questions are always welcome.